Okay, so why is it necessary that we learn anything about intermolecular forces in nanoengineering and chemical engineering? It seems like, why should this be a required course? Like, intermolecular forces, okay, van der Waals, done. It turns out that knowledge of intermolecular forces could take up, you could have an entire year on this topic. Like you could probably have a 4-year curriculum on this topic, because what it really is using non-covalent chemistry, so the attractive and repulsive forces between molecules and objects that do not involve the formal sharing of electrons, as is the domain of chemistry. Now, biological systems, sure, there are parts that are based on covalent sharing of electrons and covalent bonding, but the vast majority of processes are actually mediated by enthalpic and entropic effects that do not require sharing of electrons. So these are all a physicist's bond, electrostatic bonds that don't involve sharing of electrons. And even beyond the theoretical interest in this topic as a practitioner of nanoengineering or chemical engineering or chemistry, do we have anyone from the chemistry department in the class? How about chemistry degrees from undergrad or MS? Cool, a few people. I totally forgot where I was going. The physicist bond is a little bit different, but it's equally as important, especially in explaining day-to-day phenomena that we see. For example, how do Scotch tape and geckos stick to walls? So the answer, I heard it, van der Waals forces. That's the answer 50% of the time in this class. So you can all go home now and get the median score. How does a sandcastle work? What do you need to make a sandcastle? Water and sand. How much water do you need? 55%. Sure. So can you take a sandcastle and can you dunk it in water? Does it stay a sandcastle? Or a sand sculpture, a sand butt print? No, it doesn't stay in water, right? Because of a force called capillary forces, which are a manifestation of van der Waals forces, and in particular, a special van der Waals force that is especially strong in water called hydrogen bonding. Why is soap slippery? So if you have a little tiny bit of soap, like 1% or 0.1% soap in water, and you put it on a surface, and the surface feels slippery, why does that happen? Repulsive forces of some kind. And this is a type of repulsive force that is actually entropic in origin, which is the ions, the counter ions from the soap. So soap is SDS, sodium dodecyl sulfate, and the sodium ions float away a little bit from the dodecyl sulfate, and the confinement of those ions actually pushes the surfaces away, even though van der Waals forces you would expect based on van der Waals forces that the two surfaces would come together and stick, just like they do in Scotch tape on a wall or gecko feet on a wall. Based on our ideas of van der Waals forces and how powerful they are in biological systems, you would expect that the cell would just collapse on itself. I mean, it's mostly like there's a lot of water in there, but there's some huge fraction of it is proteins and lipids, and you would expect if van der Waals forces were so powerful, they would just, all the cells would just, how's that go again? One more time for emphasis. Cells are stable, milk is stable. Milk has little tiny particles of fat globules and proteins that scatter light. That's why milk appears white. Now, why doesn't all the milk just flocculate? My favorite word in science. Why doesn't it all just flocculate? Well, there are repulsive forces based not only on the ionic repulsion, the so-called electric double layer repulsion between the particles, but also based on the fact that milk fat globules have these protein polymer chains that produce another type of steric repulsive force, like moving two spheres together that have strings floating off of them, and you move them closer together, and because you're confining the motion of these floppy strings, i.e. polymer chains, then there's an entropic repulsion because you have fewer ways to arrange the polymer chains when they're close together and more ways to arrange the chains when they're farther apart. So you create a difference in potential energy as you separate the particles and therefore a repulsive force. So once you're done with this class, so the idea really is to strengthen your intuition in these areas. When you see a nanoscale or even a macroscopic phenomenon, especially macroscopic phenomenon, why does my finger, hopefully this works, stick, oh, almost, I almost picked it up. Okay, well, not quite. But anyway, it almost picked it up. That's capillary forces, right? And this can all be explained due to the cost of electrostatic potential energy by enlarging little bridges of sweat and humidity, because it's freaking 85 degrees in here, between your fingers and the object that your hand is sticking to. Okay, so let's do a little primer on major concepts in the course. So in professor school, just kidding, there's no such thing. They teach you to teach from the top down. So you give the bins to the class at the beginning, into which the facts later on in the class go. And that's what we're going to do now. We're going to do the whole course in however much time we have left, and then each lecture afterwards we're going to be filling in the details, but at least you'll know where we are going. Okay, this is a positive and negative charge in which the center to center distance is lowercase r. Lowercase r in this course always refers to the center to center distance. We're going to use another variable later in the course, d, capital D, which means the distance between the surfaces of particles. This is the center to center distance, and we use it when we're talking about small particles like atoms and molecules. And we have an expression for force as a function of center to center distance. F of r equals minus dWr over dr, where little w is the potential function, meaning, of course, it's almost a function. It's potentially a function. No, it's the potential energy function. The potential energy function, little w. And what does this tell us? It tells us that there is a negative or attractive force if the potential energy goes down as the separation decreases. Positive and negative charge. Can we agree that if we take these two particles and we move them closer together, the potential energy goes down? So the electrostatic potential energies of these charges decreases. And if they decrease with respect to distance, then we get a negative or attractive force. So the negative or attractive force decreases I want to say decreases, I want to say becomes more negative. More negative as positive and minus charges get closer. Is the absolute value of the energy meaningful? So if I tell you that the potential energy of some two-particle system is 5 joules, does that tell you anything about the force? Does that tell you anything about whether or not it's favorable or unfavorable? It doesn't. Only the rate of change with respect to some geometrical change, the rate of change of the energy. So if two particles come closer together and the potential energy goes down, becomes more negative, then the attractive force becomes stronger. So our absolute values energy, absolute values of potential energy meaningful? The answer is no, just the rate of change. Or the force. Already, I think we've reached a fairly interesting philosophical point, is in that a positive and negative charge, at least I think this is interesting, maybe you think it's trivial. The positive and negative charge, if you take a snapshot, an infinitesimally short window of time, you take a snapshot, is there a force, even though we're not sampling any separation? Like if we're not sort of rocking the separation back and forth, do we know if the potential energy is going to go up or down? Probably we do. Probably this is just a limit of my understanding, not human understanding. But I think there's a little bit of an interesting paradox here. So what came first, the force or the energy? Okay, I have to get used to using these things and not crushing my fingers with them. Okay. I have the feeling it's going to go all the way up, despite the increase in potential energy. Okay. All right. Okay, fine. All right. So, never mind. This is monologue time. Picture two uncharged molecules. Picture two uncharged molecules. They're at room temperature in a vacuum, two uncharged molecules. Is there an attractive force between those molecules? Yeah. There is an attractive force. Is there ever a negative, or is there ever a repulsive force between these molecules? They're just uncharged in a vacuum. They can be any two molecules spinning freely. How about oil and water? Someone who has not taken my class, any of my classes before, do oil and water must repel, right? Because there's something called a hydrophobic effect, which we've all heard of. We've all seen the way that salad dressing separates in a bottle in the refrigerator, hopefully. And so these oil and water must repel, right? Oil and water don't repel. If you just have one oil molecule and one water molecule, there will be electrostatic forces that draw them together. How far together will they get? Will they collapse into each other and just kind of become one super heavy molecule in the center? No, they won't, because of something called the Pauli exclusion principle, which says that electrons can't occupy the same volume and have the same 4 quantum numbers. So you can't have a water molecule and an oil molecule, say octane or something, come together and occupy the same space. So there's a limit to the attractive force, but all uncharged molecules do indeed attract in a vacuum if they are allowed to rotate freely. That's an important distinction. Because why? Because you could imagine if you were at absolute zero and you froze all molecular motion and you had two dipoles that were oriented toward each other, they would repel, even if they were in a vacuum. We're going to try this again. Okay, so intermolecular forces and we're going to call this IMFs. And rule number -1, nobody's going to call it that but me, but rule number -1 is the Pauli exclusion principle. Also known as steric repulsion. Andrew, would it be possible to find the thermostat in here? I have no idea where it is, and I'm sure it's not connected to the system anyway. It's just for show. Okay. Rule number 0. Rule number 0 is Coulombic. Charge, charge. Or charge dipole. So this could be water and beryllium 2+ or something like that. Now we get to the big 3. I wanted to start at 1, but I needed to get this housekeeping out of the way at the beginning. We start at number 1, which is the dipole-dipole force. And we also call this, we name this after the person who did the initial work on the dipole-dipole force, and that is Keesom. What is the dipole-dipole force? The dipole-dipole force is the force that you get when you have two dipoles. It's a little more subtle than that. The dipole-dipole force, imagine you have two dipoles that are spinning, and the spinning depends on the temperature. The rate at which these molecules spin depends on the temperature. So if you have a lower temperature, you have a lower temperature, some of these orientations will be more favorable than others. So at some point, transiently, the dipoles will be aligned in such a way as to maximize their electrostatic attraction. Maximizing their electrostatic attraction is equivalent to saying lowering the electrostatic potential energy. So there will be some geometries that are more favorable than others. So if I use, all of these chalks are broken, but suppose, I need a good long piece of chalk. Okay, two dipoles. At a high enough temperature, they are spinning kind of out of control. There's no preferential alignment. Lower temperature, they don't have as much energy to rotate, so there are some orientations that may be more favorable than others. You may get one, oh, it flipped around and whatever, but now it's back. So there's going to be some distribution that is going to maximize, it's going to balance the electrostatic energy. So you're going to minimize the electrostatic energy, but you're also at the same time, you still have to move a little bit because there's some temperature, there's going to be some entropic, some Boltzmann distribution of states given of conformations of rotational configurations that will exist at a certain temperature. Lower the temperature even more, and the distribution of allowed rotational configurations is lower, so then you'll have an even stronger attractive force. So there's some subtlety here regarding the ion dipole force, regarding the dipole-dipole or Keesom force, and what it leads to is that the Keesom force is the only one of the three so-called van der Waals forces that has a dependence on temperature because of its effect on the rotation of dipoles in an electric field produced by an adjacent dipole. What's next from 10th grade chemistry? The Debye or the dipole-induced dipole force. And this is called either the inductive or Debye force. Incidentally, the Keesom force, dipole-dipole force, is also known as the orientational force. Orientational, Keesom, dipole-dipole, all the same thing, dipole, induced dipole. What is special about the Debye force or the inductive force? Where does it come from? Well, suppose again you have a dipole and you have some non-dipole molecule. Say this is water and this is xenon in group 8, noble gas, spherically symmetric, almost, no, not quite. Okay, pretty much a floppy sphere. Okay, and you have this molecule that's rotating, and at some point along in some orientations, you're going to cause the electron cloud to either be attracted by the electric field produced by the permanent dipole, and that dipole is going to be transiently created, and as it's transiently created, this induced dipole, that is just the deflection of the electron cloud away from the nucleus or toward the nucleus or up or down, is going to create a reaction field that in turn attracts the original dipole to it. And that is the Debye force. The third, and actually most important of the van der Waals forces, is the instantaneous dipole. So you're really going to write instantaneous dipole twice? Yes. Instantaneous dipole, instantaneous dipole. Or the dispersion force named by London, which in this case is a person, not a place. Okay, together these three form the van der Waals force. And from this point forward, we're going to abbreviate it VDW force. And what is special or diagnostic about a van der Waals force is that the potential energy function is minus some constant over r to the sixth. So there is it's a very strong force when the species are close together, but it drops off very rapidly with increasing separation, hence the r to the sixth. Okay, we're all good with examples here. I think there are some exercises on the homework just to kind of get your feet wet. They're super easy, like carbon monoxide would be dipole, have a dipole. However, is it possible to have a London dispersion interaction but no Keesom interaction? Is it possible to have this but not this? Someone just say yes. 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 Name two molecules that have this but not this. CO2, CO2. CO2, CO2, CO2. So no permanent dipole. It has an instantaneous dipole just because anything with an electron, anything made of protons and electrons, so anything, can polarize another object that also has protons and electrons. And how does that work? Because electrons buzz around like a like planets around a sun. Of course, that's everyone's conception of the way atoms are built. So it literally moves around like a Ferris wheel. And at some point, just kidding, it really doesn't. And the dipole is moving along with the electron. So the dipole is pointing around this circular orbit, right? And as that dipole moves, it creates a dipole in an adjacent electron cloud. And then there's a reaction dipole again that causes the two species to be attracted to each other. It's actually the same as in the Keesom interaction, except in the Keesom interaction, we're not talking about the electron clouds, we're talking about movement of the dipoles themselves, orienting the nearby dipole. So it's actually the same effect electrostatically, but it is a different part of the molecule that's producing the effect. But since all molecules have protons and electrons, they always have the dispersion interaction, but they need a permanent dipole. They both need to have a permanent dipole in order for the Keesom interaction to be present. And for the dipole-induced dipole or Debye inductive interaction, only one of those needs to be present. So only one of the molecules needs to be a dipole, a permanent dipole. So you always have this, you sometimes have this, and this is the most restrictive case. So it's impossible to have this without, it's impossible to have this without also having this, and it's impossible to have this without also having this. Okay. Now, I don't know about you, but I don't go around measuring the forces between molecules that often. Usually we're talking about surfaces. Usually we're talking about nanoparticle suspensions, predicting the stability of nanoparticle suspensions, predicting the adhesive force of a film on a thin sheet, say for printed electronics, or the adhesion of an object to the skin for wearable bioelectronics. So these are the sorts of things that we generally care about in the lab. So how do all of these forces manifest on nanoscopic and macroscopic objects that are made of collections of atoms, not just a small handful? So then all of these forces combine to form the surface forces. And in this case, little w is now big W, and little r is now capital D. Now in this case, this was the center-to-center distance. This is now the distance between surfaces. Why distance between surfaces? Because it doesn't make sense to talk about center-to-center distances. If I want to predict how much adhesive force there is between my finger and this piece of paper, we're not going to use an expression that is the position of my heart to the piece of paper, right? We only care, we're going to talk about the most convenient form. The potential energy is going to be pretty similar. We just use capital W because we want to emphasize the fact that these are large surfaces and not just atoms and molecules anymore. Okay, so the number 4 force will be the van der Waals force between surfaces. Number 5 will be, okay, van der Waals forces between surfaces. This is literally derived assuming that all of these Keesom, Debye, and London forces are pairwise additive and you can add up the interaction between one atom in a surface and all of the atoms in the other surface and just integrate this over two surfaces and you get some force. The next force that we've alluded to before is the electric double layer, or EDL force. The electric double layer force is generally important in water. It's always important in water. It only really manifests in water in highly polar solvents, but water is the most important, so all our examples will be in water. When you put an object into water, it becomes charged. If there are acidic or basic groups on the surface of the object, then by Arrhenius chemistry, it either adopts a positive or negative charge just by virtue of the fact that it's in water, which is so easily ionized. Sometimes you could have reactive chemistry on the surface. Or sometimes, because of the auto-ionization of water, some ions just stick to the surface. So you almost always have an electric double layer of an ion that's bound to the surface and one that kind of floats away some distance away from it. There's always this diffuse layer of counterions on the surfaces, and when you compress them together, you're compressing the diffuse double layer of counterions, which produces an entropic or osmotic repulsive force that pushes those surfaces apart, and that's called the electric double layer force. Together, the van der Waals and the EDL force are called the DLVO force. Which is what you need to predict the stability of a colloidal solution. So solution of, or a suspension of nanoparticles, you predict whether or not it's going to be nicely dispersed, thermodynamically stable, or if it's going to flocculate or coagulate into some mess that connects it, that condenses at the bottom of your kitchen drain. In some cases, the electric double layer force is not sufficient to keep all of the particles from collapsing on themselves. So sometimes engineers use steric polymer-mediated forces. Which work largely the same way as the EDL force, except that instead of a cloud of counterions, you have a cloud of floppy polymer chains. And as you move particles together that are covered in these polymer chains, the polymer chains compress and they lose their entropic freedom. They lose the number of configurational states that they can occupy just because they're closer together, and therefore that entropic force pushes them apart. Both the EDL and the steric polymer-mediated force are entropically driven. Then we have some other effects that are manifestations of the intermolecular forces, like capillary forces, which depend on the van der Waals forces between molecules in a meniscus between two surfaces. What is a meniscus? If you have 2 grains of sand and you have just the right amount of water, you'll get a meniscus that's shaped like this. You can form your own meniscus at home with a little droplet of water between your finger. And you can actually feel pulling it apart is a little bit like pulling on an elastic band. I mean, you have to be kind of sensitive, but I've convinced myself that I can feel it like a little elastic band. And why does it feel like an elastic band? Because as you enlarge this surface area, you are forcing, by pulling these objects apart, you're forcing molecules in the interior of the meniscus to go to the surface. And they don't like that because they lose their van der Waals forces and hydrogen bonds with the molecules in their immediate vicinity. When they go to the surface, then they have these unsaturated valencies, and hence a higher electrostatic potential energy because it's not being lowered by molecules in the bulk. So that's the origin of the capillary force and surface tension. That's how sandcastles are made, exactly like that. You take that image, bring it to the competition, you can make a great sandcastle. Number 8 and final, although there will be more examples as we go through the course. We have friction and lubrication. Friction and lubrication depend on all this stuff. Friction and lubrication are kind of loosely, I don't know, loosely defined, but there's a lot of subtlety in the way we define friction and lubrication, or the way that friction and lubrication arise could be because of if you have just two single crystals that come together in a vacuum and the lattices at the surfaces are perfectly commensurate, you'll have friction due to the atoms in the surface hopping over each other as you drag the surfaces across. But if you have like some junk on the surface, like sandpaper, you're talking about scales that are much, much greater, like millimeter scale in some cases. Lubrication could be from a variety of sources, like the electric double layer force. For example, why is a very dilute solution of soap slippery is different from why if you take, and that's because of the EDL force. It's different from if you take the bottle of soap and just dump it on a surface. That's slippery for a different reason. That's slippery not only for the EDL force, but to a much greater extent, it's slippery because soap is viscous, and really what you're doing is measuring the shear viscosity with your finger, and that's why it feels slippery. Okay, in all of these cases, what we are trying to do, or what nature is trying to do, not with any agency, but just because it's what nature does, is to try to minimize some potential energy function. So in the case of single molecules interacting with single molecules, the potential energy function is just W of R. But if you add them up in a big system, we're talking about a potential energy function like a free energy, like we learned about in physics and chemistry. So, nature's goal is to minimize potential energy function. So what's an example of a potential energy function that we learned in our previous lives? How about the Gibbs free energy? Delta G equals delta H minus T delta S. And maybe this course will give us a clearer idea about what delta H and delta S actually are. Because when I was in high school and college, I just kind of thought, I don't know, there's something called entropy and I guess it increases. Delta S is the number of statistical microstates available. Or since I've circled the delta also, it's the change in the number of statistical microstates available under the constraints in the case of delta G at constant external temperature, or constant temperature and pressure. And delta H is the overall change in the electrostatic potential energy of the system, if we're talking only about a physicist's bond. It also includes all the chemists' bonds as well, where the electrons are actually being shared between nuclei. So this is the change in electrostatic potential energies of every component in the system. So at the beginning of the class, we will be talking primarily about interactions that occur in vacuum or in air. But in reality, these interactions are occurring in solvent media. So you have to keep in mind that in a solvent medium, you can never affect some nearby particle without also changing something that happens to the solvent. While we have a bias toward considering everything in terms of the substrate or the solvent or the protein or the nanoparticle, the solvent molecules say, hey, we matter too, just as much as the thing you put in the solvent. So including solvent. Okay, just to show you, in all of the scenarios we'll be talking about in class, we're going to be at constant temperature and pressure. So just as a little review here, the Gibbs free energy is equal to the change in internal energy of the system plus the pressure volume work done to bring the system into existence minus T delta S. This whole thing is delta H. However, we're not going to be considering systems with changes in volume, so we can always essentially say that this is 0. And just as a reminder, probably not from chemistry, but from physics, you learned about something else called A, which is the Helmholtz potential energy, which is delta U minus T delta S. So this is Gibbs, and this is Helmholtz. And they are the same for all intents and purposes in this class because we're going to be at constant temperature and pressure. Okay, any questions about anything that I said so far? These are the bins, and then the rest of the course will be the details. So we're going to cover manifestation. So we're going to do basically a derivation and conceptualization of the equations that give you the energies for all of these forces. Then we're going to talk about some applications. And that's basically how each of the 80-minute lectures will be structured. Any questions? Yeah.
For the surface forces, you put that they formed by this DLVO forces. What is DLVO?
DLVO is the name of 4 people that did the original work on it, and I'm not going to write their names down.
So the subscript T, that's constant temperature, right?
Yep, the subscripts refer to constant temperature. It's very rare in the course that we're actually going to be using, we're never going to be using A's, sometimes we'll use G's, but usually we're going to be talking about pairwise interactions, so little w's and big W's. And then we're just going to make the leap that if we're talking about a big system, you have to take into account all the little w's and all the big W's between all the components in the system. Yeah.
So for number 5, that force only happens when you dissolve something in water?
Yeah. So the electric double layer force only happens when you have something charged in a solvent. In water, anything you put in water is going to become charged.
And then why they become repulsive when you push them together? Why isn't it like have the ion and ion also like opposite charge? Like why don't they attract each other when you push them together? Why they push them?
That's an excellent question. The reason is anytime you have a size disparity, the entropic force is going to be between something that has charges on the outside that's big and tiny little charges on the inside. One, the system is electrically neutral, so there can't be any electric repulsion. The repulsion actually exists because the small charges are mobile compared to the big charges. It's like Winnie the Pooh with honey covered in honey having bees swarming around him. The bees are very fast, while Winnie the Pooh is slow. And as a result, the entropic repulsion between the bees don't want to be confined. So the system will actually relax, or it will reduce its potential energy by allowing the bees, or the counterions, more configurational states to occupy. And they can't do it if they're close to each other. Once you overcome the electric double layer force, though, there's a van der Waals force, and the van der Waals force will encourage attraction. The key is to be, if you're designing, for example, a system of nanoparticles or a paint suspension or drug delivery nanoparticles, you need to be in the range where the electric double layer force is stronger than the van der Waals force at a normal interparticle separation. You need to create a barrier, a potential energy barrier that the particles don't want to, they keep ramming against each other. You don't want to get over that barrier so that they just suck together by van der Waals force. Good question. Okay, I want to say a few things about molecules. I know this will be a little bit annoying to a few people in the room. That's totally fine with me. But because this is a course on intermolecular forces, we have to do a little bit of housekeeping on the molecular part and how we write, name and draw molecules. Because if we don't know that this is ethane, we might have a slight problem, but we won't in 10 minutes from now, I promise. Those of you who have seen this a million other times can fall asleep right now, but this is how you count to 10 in organic chemistry. How many of you did not know that? Okay, you're never going to admit to this. I'm going to assume just blink like this if you didn't know that this was ethane. You liars. Okay, number of carbon atoms. I'm going to do this really fast, and then I can let you go and enjoy the first day of school. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we use the prefix meth, eth, prop, but, pent, hex, hept, oct, non, dec. If we have something that is bonded to something that we don't, that could be anything, sometimes it's written just as a squiggle, sometimes it's written as an R, then this is a methyl. If it's bonded to an H, then it's an alkane, so it's methane. And by the power of human machine learning, these same rules apply to all of these prefixes. A few functional groups that may or may not appear in a molecule. An OH is called an alcohol. A C double bond O bonded to an OH is called a carboxylic acid. An NH2 is called an amine. This is called an amino acid. This particular one is glycine. No, we're not going to go there. Yes, we are. Wow. There is nothing right about this board. Did we ever find the thermostat?
My memory of this room is we just have to find something to pop the door.
Okay. All right. Okay. All right. Okay. While organic chemistry, I don't like to use the word organic chemistry in a course on nanoengineering. Let's just say in molecular nomenclature, we never draw the carbon atoms and the hydrogen atoms. So 1, 2, 3, 4, 5, 6, 7, 8 is octane. Sometimes things have common names. Like this is not 1,3,5 hexatriene, it's benzene. Sometimes when we have alternating single and double bonds, in some cases, but not all cases, we just draw a circle, and that's it, because these electrons move around. Okay, now we're back to some place where we might not already know, but maybe we do. How about bond strengths? Often in this class, we'll get to a point where we talk about the how the bond arose, how the intermolecular force arose conceptually. We'll derive the equation for it, describe some applications and some manifestations in everyday life or nanoengineering and chemical engineering. And we'll also talk about the bond strengths. And the bond strengths could be in units of energy, like joules, typically somewhere like 10 to the minus 20 joules or something. Or we could talk about them in terms of kilojoules per mole. So let's say C, carbon-carbon, carbon-hydrogen, and carbon double bond carbon. These are examples of covalent bonds, and they're around 346, 411, 602, and these are all examples of covalent bonds where the electrons are actually shared between the atoms in the molecules. How about NaCl? This is ionic. 500, around the same as a covalent bond. If you convert this to force needed to separate these bonds, this is on the order of nanonewtons. Yep.
The second one there, is that C double bonded with H? Or
C double bonded with
R?
C single bond H. Sorry, good point. I hope the people watching on YouTube didn't already send me an angry email. hydrogen bond is a special type of orientational or Keesom interaction that's especially strong. And the common H bonding partners are, of course, water, and this is around 25 kilojoules per mole. And how about van der Waals forces like argon-argon or methane? Methane or how about an alkane-alkane? And this is per CH2 unit. And these are all van der Waals bonds. So these are chemists' bonds, and these are physicists' bonds. And they're going to be in the single kilojoule per mole range. How much energy is available at room temperature? Use this KT to talk about single interactions between single molecules. Sometimes we use RT if we're talking about moles of molecules. That's the thermal energy, the energy that's kind of just around in the environment to make stuff happen. And if the object is to break these bonds, you want to be some good bit higher than KT or RT. RT is about 2.5 kilojoules per mole. So van der Waals bonds are not really going to be persistent. That's why argon and methane are gases. But if you have, for example, this is hexane. Hexane is a liquid, and it's got, some multiple of these pairwise interactions. Multiplied by 2 or 3 kilojoules per mole, that's going to be enough above RT. Say like a factor of 5 to 10 RT makes that bond persistent at room temperature, little RT. Not big RT, which is the universal gas constant times the absolute temperature in Kelvin. Any questions about anything before we have a good rest of the day, and I'll see you on Tuesday? Yep.
I'm asking about the attendance for the lecture.
Yes. Please come to class.
I noticed there's problem session on Friday. Is there mandatory or just the office?
It's not a problem session. I mean, that's the only way administratively I could book the room, but I will answer questions that you have. That's my office hour. On the schedule, that time, Friday 3 to 4, is my office hour. Good question. All right. Is that a question? No. Okay. Thank you.